Here we go, Ignite students. Let's have a good day today. All right, last time we talked about electromagnetic spectrum. We talked about the whole spectrum from radio to gamma rays. All right, everything. Today we're going to focus in a little bit on infrared to start. But before, let's get to a big question. Big question. What is the sun made of? And how do we know that? All right, let's see if we can get to there. We're going to back up. We're going to build our base here. So if you had two objects, you had a bar of aluminum and you had a bar of steel, and you go to a furnace, you go to a smelter, and you put them in there, you're going to start melting them. All right, and you pull them out a short while later, and they're both glowing hot. What color are they? And are they the same color? The interesting thing is they are the same color. We're not talking anymore about light reflecting from the room or the sun off of that and bouncing to our eyes. Now we're talking about the light that they emit because they're glowing hot. We say they're red hot, they're white hot, right? You go to a stove, you turn on the burner, it's a dull red, and then it goes to an orange, and then to a brighter white, and as it gets hotter. The color that's emitted does not depend on the element, it depends on the temperature. Depends specifically on the temperature. Here's our first example. This is called a Blackbody curve. So if you had something that was matte black, not reflective, not shiny, it would emit this ideal curve. The curve would very closely match this shape. Real objects, there's a little bit of difference. We're not going to worry about that. These are Blackbody curves. And so we've got intensity on the y-axis, and we've got frequency increasing on the x-axis. Why did I trip up there? Because this graph also includes wavelength. Wavelength is short here and long over here. That's just a reminder that radio is over here. Radio, microwave, infrared, visible light, which is Roy G. Biv, ultraviolet, X-ray, gamma ray. Going this direction, we're increasing frequency. Going this direction, we're increasing wavelength. So, a couple things to see. 300 Kelvin is about 0 degrees Celsius. It's 4 degrees Celsius, I think. Okay? So, just above freezing. 1,000 Kelvin, 4,000 Kelvin, 7,000 Kelvin. The temperature of the surface of our sun is basically 6,000 Kelvin. As these temperatures increase, two things happen. One, the total amount of energy, the size of underneath this curve increases. Two, where it peaks moves to the right. It moves towards higher energies, higher frequency light. So the Blackbody curve shows you that something that is nearly frozen doesn't emit any visible light. Well, that makes sense. Ice cubes don't glow hot. But something at 1,000 degrees Kelvin would be it emits lots of infrared light, but it also emits a little bitty bit of red light. So you might get a dull red glow. Something that's 4,000 Kelvin emits plenty of infrared heat, but it also peaks. The color it emits most at is this right here in the strong red, and it emits all the colors. So it might be, remember, we mix all these colors, we're going to get to white hot. This is a star. It's going to be even brighter. It's definitely going to look white, if not blue. All sorts of these things, okay? So, the higher the temperature, the more energy, and the bluer or the higher frequency of the overall, of the peak wavelength. Here we go. We've got a little galactic gas cloud here. It's about 60 Kelvin. It's a really cold cloud sitting out in the middle of the space. At 60 Kelvin, emits a bunch of radio waves, maybe a little bitty bit near the microwave, not much else. Here we've got a brand new, young, hot star. Well, it's actually not that hot. It's dim. It's just been formed. So it's 60 Kelvin. This is 600 Kelvin. This is where it peaks. This is our sun, 6,000 Kelvin. This is the black body spectrum of it. This is a galactic cluster. All right. It is it's Messier 2, 60,000 Kelvin. It's a group of really, really hot, bright stars. So on average, it comes over here, and you've got all this going on. Okay. Cool. That's a blackbody curve. Nice and simple. All right, we need to shift now. And I want you to think for a second. If you were to stand next to a pond and drop a rock in it, dink, 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 and you've got waves going out, and they're nice and even and smooth in these ripples, okay? And there's a person on each side out here, okay? This person is going to move towards you, and this person is moving away from you. And these ripples, dink, 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 are moving outward. The person who's moving towards the ripples is going to hit the first one, but instead of even space between each one, if he's coming towards you, he's going to go bink, 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 and cross all of them really fast, right? Person over here is moving away from you. Bink, 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 bink. But if he's moving away, the first one gets to him, and then because he moves, now the second wave has to chase him, so it's going to spread out. Bink, bink. It's going to be longer times between each wave hitting them. That is the Doppler effect in a nutshell. It also works if you were moving along the shore and they were standing still. It's a little different look. But for right now, we're going to focus on a stationary source and we're going to focus. I said that backwards. That's an example for a stationary source. It works the other way for a moving source and a stationary observer. All right. We'll look at another example for it in a second. We are talking about this because we talked about all the light last week. Well, it still is waves. So what the Doppler effect that works with sound works with light. Here we go. Here's our quick. That's 12. We need 15. Right here. Boom. Okay. Right here. If you've got a star, and instead of clap, 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 or dunking the rock, whatever, it's emitting light, and that light has waves. So if here's a wave 1, 2, 3, 4, if the observers are out here in their spaceships, they see these waves 1, 2, 3, 4 at a regular distance apart. If the star, this time is the star is moving. So if you were walking along the shore and you dropped your rock and then dink, 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 you had a pole and you hit the surface of the pond in 4 different spots, 1, 2, 3, 4. Well, 1 you did a long time ago, and that wave has traveled all the way out. That wave is here now. And then you took a step forward and you hit the water here at 2, and that wave travels all the way out. But it's centered where you were when you hit that pond right there. And then 3, and then 4. So the circle's 1, 2, 3, 4. Now, instead of the boats moving, like in the pond example, now let these guys stand still. Look over here. These waves are really close together. This guy's going to hear ping, 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 and it's going to have a high frequency, and it's going to look bluer. Because remember, we're talking about light, not sound. So it's going to look bluer. It's going to shift to a higher frequency on that chart. This side is going to be redder. It's going to shift the other way on that chart. With a moving source, the Doppler effect works for light. Okay, Doppler effect. That's the simple version. We're going to apply it in a minute. I'm giving you all these little parts, and we're going to bring it around, okay? So, here we go. We're going to move to the coolest thing in astronomy. One of the most important tools in all of astronomy is spectroscopy. Spectroscopy is analyzing the spectra of stars or gas or light. You could do it on Earth in a crime lab, or you could do it with a telescope in space. Spectroscopy is examining light sources to see what an object is made of. And that's it. Okay. First thing we can do, we can have a continuous spectrum. Okay? This guy right here. Here we go. There's a light for you. I'm going to take this little thing here, and 1, 2, and there we go. We've got a nice little rainbow on the edge of that fluorescent light for you right there. Okay? That's all it is. This is not a prism. This is a diffraction grating, but it shows you that white light is actually made of several colors. All right? With fluorescent things, there are a couple of little effects here, but it's that simple. We go and we put a prism up, and this is our sun. That's a really cool image. This is Roy G. Biv, all the light we can see in our sun, and we'll talk about what's going on there. Here we go. Basic first spectrum you would look at. You take a light source that is hot, solid object. You heat this thing up like the bar of iron or whatever, and you send light, and you use a prism, and you spread the light out, and you get a solid rainbow. All the colors of the light, and it's going to look like that Blackbody spectrum, where it's got all the colors. There's all these. It's full. There's no gaps. Everything's good to go. All right. Now, what happens if we switch that up and we use not something solid that's heated, something that's real thin, and something that's an element? So this is a hydrogen gas, like a cloud out in space, and you get it hot and it starts to glow, but it doesn't look solid over here. You don't see a full Roy G. Biv. You just see individual lines. This weirdness, we've got to go and we've got to talk about the atom for a minute. Atom, all right. You got your proton in the middle. You got your electrons around the outside orbiting. Okay, neutrons in the middle. We don't care about them. Electrons orbit. Electrons can orbit close to the atom, or they can orbit further out. Okay? Electron wants to go in its nice little orbit, but if energy comes in, the electron suddenly is going, woo, a nice bigger circle. And then later it may get tired and it would fall back down. But that energy is conserved. That energy has to go somewhere. So right here, if a photon comes in and hits this electron, the electron jumps up to this excited state, orbits in that excited state for a while. Later, when it collapses or falls back down to the ground state, it will emit light. This amount of energy that comes with that light and this amount of energy that comes with that light must be identical. Not close, not off a little bit, not a loss, not in energy efficiency. Perfectly identical. Option number 2. Light comes in, this time higher energy, more violet, more blue, comes in and it gives it more energy and it jumps up 2 states. We've got 2 options. It could fall all the way back down to the ground state and give off that exact same beam of light, same energy, or it could come down a little bit, pause, and then come down the rest of the way. Each of these is a specific rung, okay? These are ladders or these are stairs. You cannot stand on the 2.5 rung of a ladder. You can't be on stair 3.5 or 3 1/3. You are on the 3rd stair or you are on the 4th stair, period. There's no option. Electrons are the same way. Electrons must be on rung 1, 2, 3 here, 4, 5, wherever. So when this energy comes in, if it's not the perfect amount, the electron won't move. But what it means is that when the electron, something gave it energy. When the electron comes down, only specific amounts of energy, going from jumping down from 2 down to 1, or 2 to 0, or 2 to 1, and then 1 to 0. Those are the only 3 amounts of energy that can be emitted by this atom. Those are the only 3 kinds of lights that can be emitted by this atom. So let's go back to that other picture right here. There it is. Hydrogen has this one, this one, this one, this one. Those are specific light colors that relate to the amount of energy released from the atom when the electron falls. And every element is different. The staircase or the ladder for hydrogen is different than that for helium, which is different than that from carbon and oxygen. They're all different. So let's look through. That's a hot one. There it is, just hydrogen by itself. So I don't recall what number I had there. There we go. Hydrogen, sodium. Sodium's got a nice yellow doublet. These are the way the atoms orbit, the set of stairs in front of that electron, the way the electrons orbit the atom, the set of stairs for the electron is this. And every element gives off a unique spectrum. So when we look at our sun, we can tell based on what lines are available or what lines are not there, what's in the sun, what's in a distant star. Well, but our sun's not one gas. Our sun's a hot object, and it's not light density, it's high density. So our sun's going to emit a continuous spectrum. Here we go. So there are continuous spectra. All right, we already saw this. These are continuous spectra. These are emission spectra. There's a third type, absorption spectra. You have a hot object that's going to emit a blackbody curve, the full radiation, and you've got this cold gas. Like, so what? You've got all this minus these individual black lines here. This cold gas, remember how in the atom picture that light came through and excited the atom, and the atom jumped up and took that energy out? That energy that it took out is exactly that color, and exactly that color, and that color. All the rest of the energies go straight through that cold gas because only the element that's in here can be absorbed those specific colors. So if you get this kind of spectrum, you don't necessarily know what this bulb is made of, but you know what this cold gas is made of. So that first picture we saw, the chapter opening picture, this one for the sun, this says the lower layer of the sun is made of all these, gives you full stuff, but the upper colder, air quotes colder, because this layer of the sun absorbs some of these things back out. All right. We can wrap this up. I want to show you one more interesting picture here, and then we're going to have to hit on this. This is a lot because spectroscopy is awesome. The Doppler effect. The Doppler effect shifts things. So if a star is moving away from us, all of these lines are shifted to the longer wavelengths. If a star is coming towards us, all of these lines are shifted to higher wavelengths. This is what you would get in a lab if you just took the hydrogen alpha, the hydrogen beta, all those lines. These are shifted, and that's how we can tell the star is moving away from us or towards us. There are implications from that. We know lots of cool things about space, and it's really spectroscopy that tells us the beginning of all of it. All right, we're going to pause there today. Have a great day.